Welcome to lesson 5.1, when are figures congruent? So before we get into this lesson, what you should realize from the chapter title here, chapter 5, is mainly based on proofs using congruence. So this idea of congruence and congruent figures is going to play a large part throughout this whole chapter. So in this lesson, we're going to lay the foundation of our definition of congruence and some of the related theorems or properties. So the first thing we want to look at is the ABCD theorem. And the ABCD theorem is actually based on a lot of what we did in chapter 4. ABCD theorem states that every isometry preserves angle measure, betweenness, collinearity, and distance. So in other words, an isometry will not change any of the angle measures, points that are between each other, the points that are on the same line, or the distance of sides or segments between points. Now, the reason that we're reviewing these properties of isometries in this theorem is because congruence and congruent figures is based on that idea of an isometry. Two figures, so if we had two random figures, f and g, they are congruent figures written, f is congruent to g, congruent sign is an equal with a little squiggly above it, if and only if g is the image of f under an isometry. So remember, isometries could be a translation or a slide, a reflection, which is a flip, or a rotation, which is a turn. Any of those still could result in congruent figures. Now, what we need to make sure we remember about congruent figures is that they would all have the same angle measure, betweenness, collinearity, and distance. Meaning all the angle measures are equal, all the side lengths are equal, and so on. And if two images, or if an image and a preimage, f and g, are under the result of an isometry, then those two figures are congruent. So if we rotate f, we spin it, we flip f or reflect it, or we slide f or translate it, it would still be congruent to g. And then another term for isometry is a congruence transformation. Because a single isometry keeps things congruent, it's sometimes called congruence transformation. If we have the same orientation, we consider the figures directly congruent. So if both are clockwise or counterclockwise, they are directly congruent. If the orientation is flipped or opposite, then we call the figures oppositely congruent. Either way, they're still congruent. So if we look at figures A, B, and C here, figures A and B are directly congruent. They still have the same orientation. I can tell that because this little half circle that jets out is still on my right-hand side in both A and B. In C, it's flipped to the other side. So figures B and C are oppositely congruent. Same with A and C, because they have opposite orientations. Everything else about the figure is the exact same, so they are congruent. So example 1 asks us, are the figures congruent? If so, state if they are directly or oppositely congruent. Also name the isometry that maps one figure onto the other. So in this case, if we're thinking about, are these figures congruent or not? Well, first, are they the same size, same shape, same angle measures, all those of the above? Yes, they are. So I know they are congruent. but I don't know if they have the same orientation or not yet. If I look at the orientation of figure WONM and then figure WXUV, I can tell by spinning one of these figures onto the other, it doesn't work. So if rotating one onto the other doesn't work, that tells me they have opposite orientations. So then, this tells me that this must be some sort of a glide reflection, a combination of a flip and a spin. So in that case, or a flip and a slide. So if it is flipped and slid, or flipped or spun and slid, either way, we have a glide reflection, which means they are oppositely congruent. Now, the more important part is when you're naming the figures. If I name that first figure starting with U to V to W to X, on the other one's name, I need to match up corresponding parts. So if I'm saying UVWX is congruent to, the U on this one matches with the W on this one, so I need to start with W. The V here matches with M. The W, in this case, matches with the N, and then the X with the O, so corresponding letters line up with the other one. So because I went UVWX, I needed to go WMNO. So then, this little box summarizes a few important properties of congruence. For any figures, F, G, and H, so if we have three random figures, F, G, and H, F is always congruent to itself, G is congruent to itself, H is congruent to itself, so we have a reflexive property of congruence. We also have the symmetric property of congruence, which allows us to flip order. So for example, if F is congruent to G, symmetric property allows us to say G is congruent to F. And then we have that transitive property of congruence, where it says if F is congruent to G and G is congruent to H, then we could say F is congruent to H because both are congruent to G. And let's look at a few of those applying and matching. So the reflexive property of congruence, which letter over here would be an example of that, would be B, something is congruent to itself. Symmetric property of congruence means we flip the order. So if PQR is congruent to XYZ, then XYZ is congruent to PQR. Flipping the order of the statement is symmetric property. Transitive property would be C if angle M is congruent to angle W, and angle W is congruent to angle G, then M is congruent to G. And then example 3 are 11 true-false statements. So we're going to go through these true-false statements and decide if they're true or false based on what we know about congruence. So in number 1, it says if F is reflected over M and results in G, F and G are congruent. True are reflections in isometry. So if one figure is reflected to the other, they are congruent figures. In 2, if the translation, the T, so a slide of F results in G, then T is an isometry, meaning F is congruent to G. If that's true, a translation is a type of isometry, so they are congruent figures. In 3, if F is congruent, or if F goes under a translation of T to result in G, and T is a glide reflection, F and G are directly congruent. That's false because glide reflections result in things being oppositely congruent. If F is the image of G under a reflection, F and G are oppositely congruent. That's true. Reflections change orientation, so they would be oppositely congruent. 5. Congruence transformation is another name for isometry. That would be true. A translation image is oppositely congruent to its pre-image. False. If we're just translating or sliding something, orientation doesn't change. And 7, directly congruent figures have the same orientation. That is true, that's the definition. In 8, if G is a rotation image of F is congruent to G. Rotation is a type of isometry, so they are still congruent. That's true. Then it says a shear transformation preserves angle measure, collinearity, and distance. That's false. A shear transformation, which we haven't really explored yet, but shear transformations are not a normal type of transformation, so that would be false. Don't worry about it too much yet. If it is a regular transformation, that's true. And 10, size change transformation preserves angle measure, betweenness, and collinearity. That is true. In a size change transformation, the only thing that's not preserved would be the distance or the size. And then it says in 11, all transformations are isometries. That's false. We know we have some, like glide reflections or shear transformations, that are not single isometries.